So in this and the subsequent videos, we'll be discussing a very important aspect of ordinary differential equation theory, known as the Sturm-Luouville theory. The general Sturm-Luouville theorem is formulated as an eigenvalue problem. Suppose you can write a ordinary differential equation of the second order as follows. You can write it as ry prime prime plus q plus lambda p times y equal to 0, where p, q, and r are continuous functions on the interval a and b. And if this equation admits values yi that solve it for lambda I, where lambda or I are separate values, then, and with some boundary condition, mixed boundary condition satisfaction given by these mixed boundary condition values, the exact form of this is actually quite important, and the proof of the Sturm-Luouville theorem, which I will not be doing here, but I will refer you to my notes, the reason for those boundary conditions being what they are become pretty apparent. So under these conditions, then you have this orthonormal relation where the orthonormality is tempered by what's called the weight function. So the p is the weight function here. So with respect to the weight function, these eigenvectors, which I'll call y sub I, I'll call them the eigenvectors corresponding to the eigenvalues lambda I, are orthonormal with respect to that weight. So this type of theorem, eigenvalue theorem, is very useful because now we can actually demonstrate several differential equations can be written in this form. So before we do that, I would like to modify our understanding of Bessel equations. The traditional Bessel equation, so I'll just write down what our Bessel's equation is before it becomes Sturm-Luouville. It does not have the scope to become a Sturm-Luouville problem because it lacks a lambda. So I have x squared minus nu squared y equal to 0, where nu is called the order of the Bessel equation. So this is what we had for Bessel's equation. Unfortunately, it does not have the capacity to look like a Sturm-Luouville problem because this nu here is completely up to us. So what we can try doing is to create a lambda. So we'll call this the modified Bessel equation, and that's x squared y double prime plus xy prime plus lambda squared x squared minus nu squared times y equal to 0. In this manner, we are working in a lambda to make it look more like the Sturm-Luouville problem and to make the theorem applicable. So there are a couple of caveats here. If lambda squared is imaginary, and that can happen, if lambda is imaginary, then lambda squared equals minus 1. Then we have to use what are known as the modified Bessel equations, known as I nu x. In many problems, this turns out to be the case. And I nu x is defined as I to the power minus nu, where I is the square root of minus 1, j nu of ix. And if nu is an integer, you cannot get two linearly independent solutions from j nu, so you'll have to use what are called the corresponding Neumann solutions are going to be k nu x, and that's given by pi over 2 I negative nu x minus I positive nu x divided by sine pi nu. So I just want to mention that because you're going to see a lot of these functions I nu and k nu appear in actual applications. So now, once we have the Bessel equation written like this, it's ripe for the picking, and we can write it in terms of a Sturm-Luouville problem. The first thing you observe is that x squared y double prime plus xy prime is none other than xy prime prime, because if you differentiate, well, actually it's let me first write what this is. This is going to be x y double prime plus x plus nothing times y prime. So I get this. If I divide both sides, if I don't do this, then I'm going to be getting a factor of 2. If I write x squared y prime prime, I'll be getting a factor of 2, which I don't want. So I'll write it like this, which means that to make this look like a Sturm-Luouville problem, I have to first divide both sides of the modified Bessel equation by x. So let me first do that. So I get xy prime double prime plus y prime. Now it looks just like that. But then the price I have to pay is write this as lambda squared x minus nu squared over x, y equal to 0. And now it starts looking more and more like our Sturm-Luouville problem. Actually, I'll write it like this: nu squared over x plus lambda squared x, y equal to 0. In this fashion, written in this fashion, there's a one-to-one correspondence between this and the classic Sturm-Luouville form, and that's ry prime prime plus q plus, okay, that's lambda there and it's lambda squared here, but no worries, lambda squared x times y equal to 0. So we know now that this looks exactly like the Sturm-Luouville problem. So the corresponding identifications are r equals x, q equals negative nu squared over x, and p equals x. That's a weight function that accompanies lambda, or lambda squared in this case. And let's just take the interval to be x1, x2, because we don't want to commit ourselves to any definite interval. So because of the fact that we have a lambda squared there, the solutions, so if you want to write the Sturm-Luouville-Bessel theorem statement, or rather statement, then it's going to be the solutions of this particular equation, which I'll call star. So the solutions of star which are given as y nu of lambda x lambda sub mx corresponding to the eigenvalue spectrum lambda m. Well, they have to satisfy the boundary conditions similar to the boundary conditions that I gave you earlier for the general Sturm-Luouville problem. So the by the way, the general Sturm-Luouville problem, the coefficients a1, a2, b1 and b2 are just some real numbers, so we don't have to worry about that. So corresponding to lambda m, subject to the boundary conditions, I'll call this ai, y nu lambda m xi minus bi, the derivative, so that's y prime nu lambda m xi equal to 0. Xi means evaluated at xi, where xi is x1 and x2. So those are the boundary conditions, and they form an orthonormal system with respect to the weight function. And so I'm going to get integral of x1 to x2, x, because that's x is a weight function, p, okay, x times y nu squared lambda n x dx must be equal to some constant cn. And I've omitted the delta function part because it's 0 for y nu not equal to y mu, and it's if y nu equals y mu, then it's equal to just Cn. Now the exact form of the Cn is dependent on these boundary conditions, and the full details of the full form of Cn is given in various references, including the notes of this course. And depending on the kind of boundary conditions you have, whether it's Dirichlet or Neumann, you're going to get a use of different cases of this. So I would urge you to carefully look at the notes to study the nature of Cn for different types of boundary conditions.